Welcome back, everyone, to this technical breakdown. Today, we're putting on our chief engineer hard hats to deconstruct something that's absolutely critical, yet honestly way too often oversimplified in electromechanical engineering. I'm talking about cable tray selection. Now, a lot of people just think, hey, it's just picking a metal gutter for wires, right? No way. It is a rigorous physics and math problem. Get it wrong, and your project's power arteries literally risk total paralysis. So we're going to dive deep into the data, and specifically, we're going to compare the IEC 61537 and NEMA VE1 standards to highlight exactly what you need to watch out for to keep your engineering foolproof. Let's get into it. Here's our roadmap for today. First up, we'll look at the real-world risks of failed selection. Then, we'll explore how specific dimensions determine project success. After that, the big one, the IEC versus NEMA standard showdown. And finally, we'll wrap up with a core guide to avoiding those nasty selection pitfalls. All right, starting off with Section 1, the potential risks of failed selection. You know, in engineering, we don't just imagine risks, right? We have to deal with physical reality. Picking the wrong width and depth combination isn't just some minor drafting error on a CAD file. It actually triggers three very real physical disasters. First, you get insufficient capacity. That's where the tray literally just collapses under the weight of the cables. Second, you see severe structural deflection, meaning you get this visible, highly dangerous bending right in the middle of a span. And third, you completely lose your fill margin. That ruins our future headroom for when the project inevitably needs to expand. And let's be real, they always expand. So let's move right along to Section 2, how dimensions determine project success. 900 millimeters. That is the massive upper limit for standard perforated cable tray widths. I mean, picture a steel channel that's nearly a meter wide. It really highlights the sheer scale of modern power demands, doesn't it? It means we have to reserve huge amounts of physical installation space. So widths typically start down at a modest 50 millimeters and then skyrocket all the way up to that 900 mark. But okay, contrast that massive width with the depth for a second. The standard depth maxes out at just 100 millimeters, going as small as 25. That's it. This typical wide and, frankly, very shallow profile means we need extreme precision when we're mapping out our 3D spatial planning. Knowing those two extreme limits, here's a quick riddle for you, something we often see out in the field. In daily design and procurement, which dimension do you think is most frequently underspecified or, just treated way too casually by engineers? Is it the width or is it the depth? If you guessed depth, you hit the nail on the head. Depth is totally the unsung hero here. A lot of engineers will focus entirely on width just so they can lay all their cables flat, but depth is absolutely crucial for preventing structural failure. When your support spans reach up to 3 meters, it is that seemingly insignificant maximum of 100 millimeters in depth that actually provides the crucial bending section modulus that strictly controls the deflection and prevents your tray from dangerously bowing in midair. Okay, so how do we actually scientifically determine these dimensions without just guessing? Well, this brings us to the IEC 61537 standard's 40% fill ratio method. Let's just do some quick conceptual math. Say your bundle of cables has a total cross-sectional area of 4,000 square millimeters. You can't just go out and buy a tray with an internal area of exactly 4,000. By standard, specifically for heat dissipation, your maximum fill cannot exceed 40%. So you divide that 4,000 by 0.4, which means your tray's minimum internal area has to be 10,000. Now, if you lock in your depth at 50 millimeters, you divide 10,000 by 50 and boom, your width must be at least 200 millimeters. See? Sizing isn't guesswork, it's just rigorous math. That brings us perfectly to Section 3, the IEC versus NEMA standard showdown. Let's look closely at this heavyweight standard showdown, because comparing the IEC 61537 against NEMA VE1 is exactly how we figure out our core selection precautions. Here's the deal. You have to understand their distinct focus. IEC 61537, which is widely adopted globally, is all about thermal management and strict fill ratios at varying temperatures. NEMA VE1, on the other hand, the core of North American standards, is hyper-focused on mechanical load and the structural integrity of splice joints. So the crucial precaution for you during selection is this. If your project follows IEC, your main concern is precise space and heat management. But if you're following NEMA VE1, your precaution shifts entirely to ensuring mechanical load performance across those really extreme spans. Let's actually map this out to real engineering environments to make it concrete. In commercial buildings where you've got tight spaces, we generally select shallow depths and moderate widths just to fit inside those cramped ceiling voids. But step into heavy industrial plants facing massive cable weights and long spans. Your precaution dictates using a heavy-duty series complying with NEMA VE1's strict mechanical load requirements, typically maxing out at that 100 millimeters deep. Conversely, if you're building a data center where massive data lines demand widths nearing 900 millimeters, well, strictly adhering to IEC 61537's fill ratio standards for ultimate heat dissipation becomes your absolutely decisive precaution. All right, let's wrap things up with Section 4, our core selection pitfall guide. To do this, let's look at a real-world manufacturer, Shanghai Xinma. Now, we're bringing them up not as some commercial pitch, but strictly as an industry benchmark to kind of test our knowledge. Think about it. A manufacturer solving these complex scenarios shouldn't just be bending metal gutters. Xinma actually manufactures comprehensive cable tray systems, busway, seismic bracing, and intelligent management solutions. Because they have the capability to span across data centers, rail transit, industrial plants, and commercial buildings, it means they have to navigate drastically different physical dimension requirements effortlessly. That's the kind of benchmark you want to look for.
And honestly, here is the absolute ultimate pitfall to avoid: failing to verify your manufacturer's standard certifications. For complex or multinational projects, relying on just a single standard rarely ever cuts it. Xinma actually provides a great benchmark here too, because their product compliance covers both the IEC 61537 and NEMA VE1 standards that we just compared, while also satisfying the British European standard BS EN 500085 and the Chinese national standard GB 31251. When you're choosing a supplier, that kind of multi-standard compliance is quite literally your strongest fortress against structural failure or a major compliance crisis down the line.
So, what does this all mean for you? Well, we've explored the extreme limits from 25 all the way to 900 millimeters. We've conceptually calculated that crucial 40% fill ratio, we contrasted the vital precautions between IEC and NEMA, and we learned the true value of multi-standard compliance. Now, think back to that potential disaster of a deformed 3-meter span just because somebody ignored the depth, or having your future capacity completely stranded due to a mismatched standard. So I'll leave you with this question. Engineers, designers, when you unroll your next set of blueprints, have you definitively chosen the right standard to build an indestructible power artery? Something to think about. Until next time, keep engineering smart.